Can device accelerometer data be used to detect the type of activity a person is doing? In this presentation, we'll present this problem as a multi-class classification problem and employ a series of machine learning techniques to answer this question. But first, why should anyone care about this problem? This problem is applicable to a diverse set of applications, for example, health and fitness monitoring. We can already see similar applications on the market, such as the Apple Watch, Fitbit, and Garmin's, and many others. These devices have onboard accelerometers which can be used to track the user's activity and provide feedback on their health and fitness. Having a model to interpret this data can be useful for retrospective analysis of the user's activity and health. Safety monitoring. This problem can also be used to monitor the safety of a person. For example, the model can be used to detect if a person has taken a hard fall or is in a car crash. The device can then be programmed to automatically call for help if the user is unresponsive. This can be very useful for elderly people who live alone. Environmental monitoring. A model can be used to detect if a person is walking, running, or driving. This data can then be used to monitor the environmental impact of the user's activity. Data like this is especially important in today's world where we are trying to reduce our carbon footprint. We use the Motion Sense dataset, a Queen Mary University of London project. They had 24 people do 6 activities: walking, walking upstairs and downstairs, jogging, sitting and standing, with 15 trials each. This was done using an iPhone 6 and the CrowdSense app at 50 Hz. This recorded the accelerometer data split into gravity and user acceleration, gyroscope and altitude data, all stored in CSV files. The trials were split into short 1 through 9 and long 10 through 15 trials, and it's all time series data. This creates a dataset with 12 features and 6 classes. This project can be approached as a multi-class classification problem where there are 6 classes. This will be solved using supervised learning techniques. In order to ensure the best results from the supervised learning models, we will use PCA in order to analyse the data and reduce the dimensionality. This will help simplify the data so the models can be trained more effectively. We will also use cross-validation to ensure that the models are not overfitting the data. This will help us ensure that the models are generalising well to unseen data. The data must first be integrated, as currently it's a big collection of CSV files. All the CSV files are concatenated together and the activity labels are also added to the data. The data is already clean, so no further cleaning is required. The data can then be split into test-train sets. The short trials will be used for testing and the long trials will be used for training. For neural network-based models, the training data will further be split into training and validation sets, 80-20 split. Some feature engineering is also required. The user acceleration and gravity acceleration will be combined to get the total acceleration. As well as this, the norm of the total acceleration will also be calculated. Is combining the user acceleration and gravity acceleration a good idea? On the original dataset of 12 features, using PCA we can see that the total explained variance of the first 10 principal components is 100%. This means that 10 features can be used to represent the data, making 2 features redundant. If we use PCA on the dataset with the combined acceleration and drop the user and gravity acceleration, leaving 10 total features, we can see that the total explained variance of the first 10 principal components is 100%. This means that all 10 features are important and none should be removed. From this, we can see that combining the user and gravity acceleration is a good idea. We will use a series of models to solve this problem and see how the models compare against each other. The models we will use can be seen on screen. We will use standard decision trees, random forests with 10 estimators, and the configuration of the neural network can be seen on screen now. As an early set of tests, I fit the models to the initial data. As we can see from the results, the models performed with a 70 to 80% accuracy. This is okay but can be improved. If we have a look at each individual category, the models performed well with the sitting and standing activities, but not very well for the others. But why is this? None of the models take into account the time series nature of the data. Activities like standing and sitting are stationary and do not require additional time series information to be classified. However, activities like walking and jogging are not stationary and require the time series information in order to be classified. How can we encode the time series information into our models? In order to add this information to our models, we can use 2 methods. Windowing slides a window of a fixed size over the data and uses the data in the window to make the prediction. The data is 10 by window size matrix, meaning that data is 2D and must be used by a model that can interpret 2D data. The other method is rolling features. Using this method, for each feature, a rolling mean, standard deviation, and median feature is calculated. This means that the data can be used by a model that can interpret 1D data. Using the rolling feature dataset shows a massive increase for all models, performing at around 90% accuracy. The graph shows the accuracy for each category of each model, with the dotted line showing the accuracy of the early models. The accuracy for the sitting and standing categories have not changed much, but the accuracy for the other categories has increased massively. This can further be illustrated by comparing the confusion matrices of the early models and the rolling feature models. The early models misclassified walking for jogging, walking upstairs and walking downstairs. This is because the early models did not have access to the time series information, which would reveal where the person was going next. The rolling feature models did have access to this information and were able to classify the activities correctly most of the time. In order to use the windowing data, we will use a CNN, LSTM and RNN with the following architecture. Since this is a more complex model, the L2 regularizers will be used alongside dropout layers to prevent overfitting the data. As we can see from the results on screen, the windowing-based models performed very well with a minimum accuracy of 94%. This is a massive improvement, however there is still room for more. The size of the sliding window can be changed to give more or less information to the model. Here, the results can be seen for different window sizes. As we can see, the accuracy increases as the window size does. This is because the model has more information to make a prediction. However, the model does have more parameters, meaning it is more difficult to train and will take longer to predict results. The confusion matrices for the two best performing models of each method can be seen here. As we can see, the rolling features method misclassified walking and jogging for going upstairs and downstairs. This could be due to the fact that the rolling features data for these activities could look too similar. The windowing method has this problem, but not to the same extent the rolling features method did. The best rolling feature model achieved an accuracy of 96.3%, while the best windowing model achieved an accuracy of 97%. This is a massive improvement over our early models. The CNN training time was significantly longer than other models, taking 10 times longer than the rolling features models. In conclusion, we have shown that the device accelerometer data can be used to interpret the type of activity a person is doing. We have also shown that the time series information is very important for accurately classifying the data. We've shown that the windowing method can be more accurate than the rolling features method, but also requires more parameters and takes longer to train. This could mean the rolling features method is more suitable for applications where computational power is limited, for example on a smartwatch. Since the windowing data is more complex, it also allows for more complex models to be used without overfitting the data. This means there is also room for improvement on the architecture of the windowing-based models. The dataset used in this project posed some limitations. It was not very diverse, meaning that the models may not generalize well to new data by different test subjects. The dataset was relatively small, meaning the models may suffer from overfitting. As well as this, the dataset is not real-world data and was recorded in a controlled environment where only one activity was performed at once. This is not the case in real-world data, where people may rapidly switch between activities. The models used in this project also pose some limitations. The windowing models also have a very high computational cost due to their large numbers of parameters. As well as this, the neural network models are not very interpretable, making it difficult to understand how and why the model is making its predictions.